My name is Jian Wu, and I will give an introduction on our work accepted by the Interspeech 2020. The name of our paper is an end-to-end architecture of online multi-channel speech separation. It's a joint work between Northwestern Polytechnic University in Xi'an, China, and Microsoft. The first author did the work when he was an intern in Microsoft STCA Beijing. The goal of our paper is to design a network which can perform multi-channel speech separation with the limited latency, and the results of the separation should improve the recognition accuracy of the meeting transcription tasks. Meanwhile, we also hope such networks can run in online model with slight performance degradation. Previously, we have one paper that addressed the same issues and proposed no-latency system that consists of two networks and utilize fixed beamformers. However, it still has some drawbacks. For example, the two networks are individually optimized, so it may need suboptimal performance. In this paper, we try to improve the recognition accuracy under such framework, especially in online situations. As a beamforming technique has been proved to be very robust to speech recognition task, we firstly talk about multi-channel speech separation with beamformer. We have two kinds of beamformers, the adaptive one and the fixed beamformers. Although the adaptive beamformer, such as MVDR, needs longer speech context to estimate the signal statistics. They have strong capability on the interference cancellation, so they always work well in the offline model when the information of the whole utterance is available. The advantages of the fixed beamformer is that it has no latency, but it is limited on filtering out the interfering signals. And also, we need source localization results to help us picking the target beam. So in the previous paper, there are four modules in it, namely the unmixing network, the extraction network, the fixed beamformer, and the sound source localization. Here, we look into the details of the UFE framework. Firstly, the multi-channel signals are passed to a mixing network, and it predicts two speaker masks, which is used in SSL module. Then the SSL will give two directions based on the mixing masks. These directions will use to compute fixed beamforming results and the corresponding angle features. Finally, the extraction network predicts target beam masks to filter out the interfering signals in the selected beam with the help of the angle feature. We predefine 18 groups of the fixed beamformer filters in total to scan from 0 degree to 360 degree. In our experience, we found several problems in current UFE framework. The error of the SSL will degrade the performance seriously in the evaluation stage, and we can observe obvious performance degradation in online situation due to the error propagation between these each models. The extraction and the mixing network cannot be joint optimized as the SSL is a non-differential operation. So we proposed E2E UFE structure to overcome these drawbacks. The main idea of the E2E UFE is to select angle feature and target beams through estimating the spatial width on all the potential directions instead of using SSL algorithm. To achieve this, we also integrate beamformer and angle feature as the part of the neural networks, and make the whole network outputting two beam masks simultaneously. The idea of such the attentional selection is very straightforward, and here we use beam features as an example to for illustration. First, the pre-separation mask E and the the set of beam features B are projected using two linear layers. VP and VB are projection layer with that converts the pre-separation mask and the beam into the some dimension D. Then a pairwise similarity matrix is defined between each frame in VP and VB using the scale dot production distance. After that, we average the similarity matrix along the time axis, and then apply softmax function to generate the spatial weights. Finally, the weight and sum operation is performed to get the selected beams. We use SISNR as the objective function, so all the STFT representation of the separation results are transformed to time domain signal using inverse STFT. For the unmixing network in UFE and the E2E UFE, the loss function is wrote in permutation invariant form to solve the permutation problem during the training. For extraction network in UFE, we simply sum up loss of each speaker together because there's no permutation issues here. We use a DAM optimizer to train the mixing and the extraction network in UFE framework with the initial learning rate 0.001. The pre-separation and extraction part of the E2E UFE is initialized from the well-trained models. So we use smaller learning initial learning rate for the joint training. In the experience, we set frame length and hop size as 512 and 256. The squared root handling window is used in STFT and ISTFT. The cosine IPT feature is computed between three channel pairs, namely channel 1 and channel 4, channel 2 and channel 5, channel 3 and channel 6. And the angle feature is computed over 6 channel pairs. The extraction network in UFE and the E2E UFE is always 3-layer unidirectional STM with 512 nodes. The pre-separation layers of the E2E are 3-layer contextual LTMs, while for the UFE unmixing network, we added the experience with 3-layer bidirectional LTM for comparison. The proposed system was trained with multi-channel artificially mixed speech. The closed talk signals were taken from two open source datasets, Interspeech and Common Voice, as well as Microsoft's internal dataset. 7 channel signals were simulated by convolving clean speech signals with artificial room impulse responses generated using the image method. The RT60 time were uniformly sampled from 0.1 and 0.5 seconds. The simulated tropic noise was added to each utterance with an SNR sampled from 10 and 20 dB. We make sure that each utterance contains only 1 or 2 speakers, and the mixing SDR is between -5 and 5 dB. The average overlapping ratio on training data is kept around 15%. We perform on-the-fly data simulation to increase the diversity of the training data. For evaluation data, we have 2 sets. The simulated data sets using closed talk data from the Interspeech testing clean set, and the semi-real data set mixed using the single speaker real recordings. Each set has 2 subsets with different overlapping ratios. One is between 20% and 15%, and another one is between 15% and 100%. We recorded the whatever rate and the SNR numbers in offline and online evaluation. The SISNR results are not included in the paper due to the space issues. In the offline evaluation, we are allowed to use the information from an entire utterance, while in the online evaluation, only one block of the speech is available. We use double buffer scheme to avoid the speaker permutation issues between the blocks, and each block has overlapping parts with the previous one. In this paper, we always use 2 seconds num block size for online evaluation. The offline evaluation results are shown in this page. The whatever rate of the mixed beam is bad due to the weak power of the interference cancellation of the fixed beamformer. We can see that the proposed E2E UFE system achieves comparable performance with the UFE on the simulated dataset and shows clear performance advantage in semi-real set, which proves the effect of the end-to-end joint training scheme. This page shows the results of the block-wise online evaluation. On the simulated data set, E2E UFE shows no significant degradation compared with the offline performance. On the semi-real dataset, it brought about a 12.47% average reduction, average relative whatever rate reduction compared with the UFE system using a 2 seconds history context. Increasing the look-back context can lead to slightly better results. By contrast, the original UFE results in much larger performance degradation for the online evaluation. One hypothesis for the rebuttalist of E2E UFE is that during the training, the E2E UFE model already optimized for the wrong beam selections, while for the UFE, only the correct beams were selected as the input. At last, I will give 2 samples selected from the semi-real dataset to show the separation results of the E2E framework.
We were trying to improve the situation in part
going back to the segment editor.
We thought we had a better model. We were trying to improve the situation in Parkview for profit speech. And we thought we had a better model.
Which means I'm going back to the segment editor tool.
Yeah, that's the introduction of our works. Thanks for the listening.